The morning sun cast long shadows across the Guidonia airfield just outside Rome as a group of Italian engineers gathered around a workbench cluttered with technical documents and performance charts. It was the spring of 1943, and the war that had once seemed so promising for the Axis powers was beginning to turn against them. The Mediterranean sky, usually so brilliant and blue, seemed heavy that day, as if it too understood the weight of what these men were about to confront. At the center of the group stood engineer Tranquillo Zerbi, a veteran designer who had spent decades perfecting Italian aircraft engines. His weathered hands, stained with years of oil and metal dust, trembled slightly as he held a captured technical manual. The document had been recovered from a downed American P-38 Lightning just weeks earlier, pulled from the wreckage near Sicily before the aircraft was completely destroyed. What it contained would shake the foundations of everything Italian aviation engineers thought they knew about air superiority. The P-38 Lightning. Even the name carried a certain electricity, a promise of speed and power that seemed almost mythical to those who had only seen it as a silver streak across the sky. All was too fast to catch, all was too high to reach. Italian pilots had been encountering these twin-engine fighters with increasing frequency over North Africa and the Mediterranean, and their reports painted a picture that troubled even the most optimistic military planners. The Lightning could outclimb anything Italy had. It could outrun anything they flew, and when it dove from altitude, it moved with a speed that seemed to defy the very laws of physics as Italian engineers understood them. But surely, the engineers reasoned, surely there had to be some exaggeration in these reports. Pilots in combat were known to overestimate enemy capabilities to make their own narrow escapes seem more heroic, to justify losses that might otherwise appear as failures of skill or courage. The numbers couldn't really be that different, could they? Engineer Zerbi looked at his colleagues, men who had dedicated their lives to advancing Italian aviation technology. Among them was Giuseppe Gabrielli, the brilliant mind behind the Machi fighters, and engineers from Fiat, Alfa Romeo, and Isotta Fraschini, companies that had built some of the finest engines Europe had ever seen. These were not novices. These were men who understood thermodynamics, who could calculate compression ratios in their heads, who had spent countless hours testing engines to their breaking points and beyond. The captured P-38 manual lay open to a page detailing the specifications of the Allison V1710 engine. Two of these power plants, mounted on either side of the Lightning's central nacelle, gave the aircraft its distinctive twin-boom configuration. Zerbi read the numbers aloud, his voice steady but growing quieter with each specification. 12 cylinders arranged in a V configuration, liquid-cooled, displacement of 28.03 liters, supercharged, maximum output of 1,425 horsepower at 3,000 revolutions per minute. The room fell silent. Someone cleared their throat nervously. Another engineer, younger than the rest, let out a low whistle before catching himself and looking embarrassed. 1,425 horsepower per engine. The P-38 had two of them. Zerbi set down the American manual and picked up another folder, this one containing specifications for Italy's most advanced fighter engine currently in production, the Daimler-Benz DB605 that powered the Machi C205 Veltro, widely considered the best fighter Italy had managed to field. The DB605 was a German design, built under license by Fiat, and it represented the cutting edge of Italian fighter engine technology in 1943. The numbers told a different story than the one anyone wanted to hear. 12 cylinders, also arranged in a V configuration, also liquid-cooled, displacement of 35.7 liters, actually larger than the American engine, supercharged as well, but maximum output, and here Zerbi's voice dropped almost to a whisper, was 1,475 horsepower. For a moment it seemed like the Italian engine was competitive, perhaps even slightly superior. But then the implications settled over the group like a fog rolling in from the Tyrrhenian Sea. The P-38 had two engines producing nearly 3,000 horsepower combined. The Machi C205, Italy's finest single-engine fighter, had just one engine producing barely 1,400 horsepower. The Lightning had more than double the power available to Italian pilots. But raw horsepower alone didn't tell the complete story, and the engineers knew it. Aircraft performance depended on a complex interplay of factors: power-to-weight ratio, wing loading, aerodynamic efficiency, propeller design. Perhaps, they reasoned, the American aircraft was heavier, less efficient, burdened by all that additional structure required for its unusual twin-boom design. They turned to the weight specifications. The P-38 Lightning, in its combat-ready configuration with ammunition and partial fuel, weighed approximately 12,000 pounds at takeoff. The Machi C-205, similarly configured, weighed around 7,000 pounds. Someone pulled out a slide rule. The calculations took only moments. The power-to-weight ratio of the P-38 Lightning came out to approximately 0.235 horsepower per pound. The Machi C-205, Italy's best, managed about 0.210 horsepower per pound. Even with its additional weight, the American fighter had a superior power-to-weight ratio. Not dramatically so, but enough to matter. Enough to explain why Italian pilots reported that the Lightning could outclimb them, could accelerate away from them, could choose when and where to fight, while Italian pilots were forced to accept whatever engagement the Americans offered, or flee if they could. The afternoon light streaming through the workshop windows had taken on a golden quality by the time the engineers finished their initial analysis. They had moved beyond simple power comparisons to examine every aspect of the two designs, looking for areas where Italian engineering might have achieved advantages that could offset the raw power deficit. Engine reliability became the next focus of their investigation. Perhaps the engineers hoped. The American engines were powerful but temperamental, prone to failure, requiring constant maintenance that would reduce their practical effectiveness in combat operations. The captured manual included maintenance schedules and recommended overhaul intervals. The Allison V-1710, it turned out, had a recommended time between overhauls of 300 hours. Some variants were pushing toward 400 hours between major maintenance. The engineers cross-referenced these numbers with data on Italian engines. The DB605, considered highly reliable by European standards, typically required major overhaul at around 200 hours of operation. Earlier Italian engines, like those powering the Machi C-200 and C-202, often needed attention even sooner. The Americans weren't just producing more powerful engines, they were producing more reliable ones. The discussion turned to fuel. Surely, the engineers reasoned, such high power output must require exotic fuel blends, high-octane aviation gasoline that would be difficult to produce in quantity, that would limit the operational deployment of these aircraft. Italy struggled with fuel supplies, with octane ratings, with the chemistry and refining processes needed to produce high-performance aviation gasoline. Perhaps the Americans faced similar challenges. The manual specified fuel requirements. The Allison V-1710 was designed to run on 100-octane fuel, though it could operate on lower grades at reduced power settings, 100 octane. Italian engines typically ran on 87 octane, sometimes stretching to 91 octane for the most advanced models. The Americans were routinely producing and distributing fuel that Italy could barely manufacture in experimental quantities. Engineer Gabrielli, who had remained mostly silent during the discussion, finally spoke. His voice carried the weight of recognition, the sound of a man who had just understood something he had suspected but hoped wasn't true. "We're not fighting pilots," he said quietly. "We're fighting their entire industrial system, and we're losing before the battle even begins." The room remained quiet for a long moment. Outside, the sounds of the airfield continued. Mechanics working on fighters, engines being tested, pilots preparing for evening patrols. All of it suddenly seemed futile, like rearranging furniture while the foundation crumbled beneath. But engineers are practical people, trained to work with the reality they're given rather than the reality they wish existed. If they couldn't match American production, if they couldn't duplicate American technology, perhaps they could still find ways to narrow the gap, to give Italian pilots better odds than they currently faced. The investigation deepened over the following weeks. More data arrived from various sources, not just from captured aircraft, but from intelligence reports, from pilot debriefings, from radar tracking stations that had logged the performance of American aircraft during combat operations. Each new piece of information added detail to the picture, and none of it was encouraging. The P-38 Lightning could reach altitudes above 40,000 feet, flying in the thin, cold air where Italian fighters struggled to operate. At those heights, the Lightning's turbo-supercharged engines maintained performance, while Italian engines gasped for air, their power output falling dramatically as atmospheric pressure decreased. Maximum speed comparisons were equally sobering. The P-38 in level flight at optimal altitude could exceed 400 miles per hour. The Machi C-205, pushed to its absolute limit at its best altitude, might touch 390 miles per hour under ideal conditions. In practical combat scenarios, the difference was often greater. The Lightning cruised at speeds that represented the maximum sustainable velocity for Italian fighters. Climb rate told a similar story. The P-38 could reach 20,000 feet in under 7 minutes. The Machi C-205 needed nearly 9 minutes to reach the same altitude. In combat, those 2 minutes represented an insurmountable advantage. The American pilot could position himself above Italian formations, could choose the moment of attack, could dive through Italian defensive formations, and climb back to safety before Italian pilots could react effectively. Range and endurance added another dimension to the disparity. The P-38, with its internal fuel capacity and provisions for external drop tanks, could patrol for hours, could escort bombers deep into enemy territory, could hunt for targets across hundreds of miles of Mediterranean waters, and return home with fuel to spare. Italian fighters, designed for point defense and short-range interception, often had to break off engagements not because they were losing, but because they were running low on fuel. The engineers examined the structural aspects of the American design, looking for weaknesses, for compromises that might be exploited. The twin-boom configuration seemed complex, potentially fragile, a design that might suffer from structural problems or control difficulties. But the more they studied the design, the more they recognized its advantages. The central nacelle provided an excellent platform for heavy armament. The P-38 carried 120mm cannon and 450 caliber machine guns, all mounted in the nose, all firing along the aircraft's center line with no convergence issues. Italian fighters, with guns mounted in the wings, had to set convergence point, had to accept that their weapons would only achieve maximum effectiveness at specific ranges. The twin-boom layout also provided redundancy. An Italian single-engine fighter with engine damage was likely going down. A P-38 could lose one engine and still fly home, still fight if necessary. Pilots reported that Lightnings hit by anti-aircraft fire or damaged in combat often continued flying when a single-engine fighter would have been lost. Even the small details revealed American advantages. The P-38 had a tricycle landing gear, making it easier to land and reducing the risk of ground accidents. Italian fighters used conventional tailwheel configurations that required more pilot skill and resulted in more training accidents and operational losses. The Lightning had a pressurized cockpit in later variants, allowing pilots to operate more comfortably at high altitude. Italian pilots wore oxygen masks and suffered from cold and fatigue during high-altitude operations. As spring turned to summer in 1943, the engineers compiled their findings into a comprehensive report. The document, classified as highly secret, made its way through military channels to planners and decision-makers in Rome and Berlin. Its conclusions were unambiguous and deeply troubling. Italy could not match current American fighter technology with existing designs and manufacturing capabilities. The gap was not something that could be closed through incremental improvements or clever modifications. It represented a fundamental difference in industrial capacity, in engineering sophistication, in access to strategic materials, and advanced manufacturing processes. The report calculated that to match the P-38's performance, Italy would need to develop entirely new engines with power outputs 50 to 60% higher than anything currently in production. These engines would require advanced metallurgy, better fuel, more sophisticated supercharging systems, and manufacturing precision that Italian factories couldn't currently achieve. Even if the engineering problems could be solved, even if prototype engines could be built and tested, production models couldn't reach operational squadrons for at least 2 years, probably longer. 2 years. By then, the engineers knew the Americans would have moved on to even more advanced designs. It wasn't a race Italy could win. It was a race Italy had already lost. But the report didn't simply catalog failures and accept defeat. Engineers are problem solvers by nature, and the Italian team proposed several approaches that might narrow the gap even if they couldn't close it completely. First, they recommended focusing on improving existing designs rather than attempting to develop completely new engines. Small improvements in supercharger efficiency, in fuel injection systems, in weight reduction could yield modest performance gains without requiring massive industrial retooling. Second, they advocated for tactical adaptations that could minimize the impact of American technical superiority. Italian fighters shouldn't attempt to engage P-38’s in climbing contests or stern chases where the American advantages would be decisive. Instead, Italian pilots should use altitude when they had it, should fight in the vertical plane rather than the horizontal, should attempt to force turning engagements where the lighter Italian fighters might have advantages in maneuverability. Third, they pushed for better pilot training, for more flying hours before pilots entered combat, for improved tactical doctrine that recognized and worked within Italian capabilities rather than trying to copy American or German methods that required performance Italian aircraft couldn't deliver. The report's recommendations were sound, but they were also received with the resignation of men who knew they were proposing bandages for mortal wounds. Better training couldn't overcome a 50-mile-per-hour speed disadvantage. Clever tactics couldn't change the fact that Italian pilots would always be fighting from a position of technical inferiority, would always be giving the Americans the first move, the choice of engagement, the ability to dictate the terms of combat. In quiet moments, some of the engineers wondered whether this disparity in aircraft performance was merely a symptom of a larger problem, whether the gap in fighter engines reflected deeper differences in how nations organized their industries, educated their workers, approached technological development. America seemed to approach engineering challenges with unlimited resources and boundless optimism, testing multiple solutions simultaneously, accepting failures as learning opportunities, scaling successful designs to production volumes that seemed almost wasteful in their abundance. Italy, by contrast, had to carefully husband scarce resources, had to make every prototype count, had to move designs into production even when engineers knew they weren't quite ready, weren't quite good enough, because time and circumstances allowed no other choice. Italian engineers were often as talented as their American counterparts, sometimes more creative, certainly more practiced at extracting maximum performance from minimal resources. But talent and creativity couldn't overcome the simple mathematics of industrial capacity and resource availability. The summer of 1943 brought the Allied invasion of Sicily, and with it, even more encounters between Italian fighters and American aircraft. The engineers' theoretical conclusions were tested daily in the skies over the Mediterranean, and the results confirmed their worst predictions. Italian pilots fought bravely, skillfully, with courage that earned respect even from their enemies. But bravery and skill could only do so much when the equipment couldn't keep pace. By August, the engineers at Guidonia were working on contingency plans, designs for fighters that might be built if Italy managed to continue the war, if new alliances could be formed, if somehow the tide could be turned. But these were exercises in theoretical engineering rather than practical development. The numbers still didn't add up. The gap remained. Engineer Zerbi, now working longer hours than he had in years, sometimes stood on the airfield in the evening and watched Italian fighters return from patrol. He could usually tell how the mission had gone before the pilots even climbed from their cockpits. The way they taxied, the slump of their shoulders, the looks they exchanged with ground crews, all told the story of fighting a losing battle against an enemy who seemed to operate by different rules, whose aircraft performed at levels that stretched the boundaries of what Italian engineering could achieve. One evening in late August, as the sun set over the Roman hills and painted the sky in shades of orange and purple, Zerbi watched a young pilot climb stiffly from his Machi C-205. The aircraft bore signs of combat. Bullet holes stitched across one wing, scorched paint where tracers had passed too close. The pilot, barely 20 years old, caught Zerbi's eye and walked over, pulling off his flying helmet and running one hand through sweat-dampened hair. "We saw them today," the pilot said, his voice carrying the flat tone of exhaustion and something deeper, something like despair. P-38’s, 3 of them. We were 8 Maquis, good pilots, well positioned. We had altitude. We had sun. Everything was in our favor. He paused, looking at his aircraft as if seeing it for the first time. They climbed through us like we were standing still, just powered up through our formation, broke us apart, and when we tried to chase them, they were gone. Didn't even stay to fight. Just showed us they could do it whenever they wanted. Zerbe wanted to offer encouragement, wanted to tell the young pilot that new designs were coming, that Italian engineers were working on solutions that the situation would improve. But engineers don't lie well, and the truth was written in the technical reports stacked on his desk, in the performance charts that told a story no amount of optimism could change. You did what you could, Zerbe said finally. You all did. The pilot nodded, not really agreeing, but acknowledging that there wasn't anything else to say. He walked toward the operations building, his parachute bag dragging behind him, looking older than he had that morning when he'd taken off full of determination and fighting spirit. As summer faded toward autumn, the political situation in Italy deteriorated rapidly. The government collapsed. New alliances were proposed, rejected, formed in confusion and desperation. The engineers at Guidonia found themselves working under new authorities, following new directives, designing fighters for an air force that was fragmenting into competing factions. Through all the chaos, the basic facts remained unchanged. American fighters were faster, more powerful, more capable than anything Italy could produce. The P-38 Lightning, with its distinctive twin-boom configuration and its Allison engines producing nearly 3,000 combined horsepower, represented a level of aviation technology that Italian industry couldn't match in any practical time frame. The comparison that had begun that spring morning when engineer Zerbe first opened the captured technical manual had expanded from a simple evaluation of engine specifications into a comprehensive analysis of industrial capability, strategic resources, engineering sophistication, and national capacity for technological development. At every level, at every point of comparison, the conclusion remained the same. The numbers weren't even close. In later years, after the war had ended and the surviving engineers scattered to new careers in a changed world, some of them would write memoirs or give interviews about their wartime work. They spoke with pride about Italian engineering achievements, about elegant solutions to difficult problems, about aircraft that performed beyond what limited resources should have allowed. But they also spoke honestly about the lessons learned from comparing their best engines to American power plants like the Allison V-1710. They had confronted the reality that modern warfare was as much about industrial capacity as battlefield courage, that technology could create advantages no amount of skill or determination could overcome, that nations fought with their factories and research laboratories as much as with their armies and air forces. The technical specifications told the story in simple numbers. The Allison V-1710 produced 1,425 horsepower from 28 liters of displacement. The Daimler-Benz DB605, Italy's best engine, produced 1,475 horsepower from 35 liters. Similar power from 25% more displacement meant the American engine was fundamentally more efficient, extracting more energy from every cubic inch of volume, every pound of fuel, every revolution of the crankshaft. But even more significant than the efficiency difference was the fact that the P-38 carried 2 engines, that American industry could afford to design aircraft around twin-engine configurations that doubled the power available, while Italian engineers had to squeeze every possible horsepower from single-engine designs because Italy couldn't afford the weight, the complexity, or the resource consumption of twin-engine fighters. The numbers weren't just technical specifications. They were measurements of industrial philosophy, of national priorities, of the different paths nations had taken through the Industrial Revolution and into the age of mechanized warfare. Italy had industrialized later than America, had smaller deposits of strategic materials, had a less developed machine tool industry, had fewer engineers trained in the latest techniques of aeronautical design. These historical factors, accumulated over decades, express themselves in the simple comparison of 2 aircraft engines. One could produce more power, more reliably from less displacement, while burning better fuel. The other represented the best that Italian engineering could achieve with the resources available, and it simply wasn't enough. The story of Italian engineers comparing their best fighter engine to the P-38 P-38's Allison V-1710 isn't primarily a story of engineering failure. Italian engineers were capable, creative, often brilliant in their approaches to difficult problems. Instead, it's a story about the realities of industrial warfare in the mid-20th century, about how military outcomes were increasingly determined by factors far removed from the battlefield itself, factors like industrial capacity, resource access, educational systems, and technological infrastructure. When engineer Zerbe first opened that captured manual in the spring of 1943, he began a process of discovery that revealed uncomfortable truths about Italy's position in the modern world. The P-38 Lightning, with its twin Allison engines producing nearly 3,000 horsepower, wasn't just a weapon system. It was a symbol of American industrial might, of an economy that could afford to design and build aircraft around principles of overwhelming technical superiority rather than careful resource management. Italian pilots would continue to fly combat missions throughout the remainder of Italy's involvement in the war, and many of them would perform with skill and courage that earned respect from friends and enemies alike. But they would do so knowing that they were fighting at a disadvantage, that every engagement with American fighters required them to overcome not just the enemy pilot, but also the enemy's superior technology. The engineers who documented these disparities, who calculated the power-to-weight ratios and compared the performance specifications, provided their nation with honest assessments, even when those assessments were painful to deliver and difficult to receive. Their work stands as a testament to the integrity of technical analysis, to the importance of understanding reality clearly, even when reality is discouraging. In the end, the comparison between Italian engines and the P-38's power plants tells us something important about how wars are won and lost in the modern age. Victory goes not simply to the bravest soldiers or the most skilled pilots, but to the nations that can field superior technology in sufficient quantities. The numbers weren't even close because the industrial systems producing those numbers operated on fundamentally different scales, with different resources, different capabilities, different approaches to organizing human effort and material resources. That spring morning at Guidonia, when Italian engineers gathered around a captured technical manual and began comparing specifications, they were documenting more than just the performance gap between two aircraft engines. They were capturing a snapshot of industrial modernity, of how nations in the mid-20th century expressed their power through technology, of how the abstract measurements of horsepower and displacement and fuel octane translated into concrete advantages in combat that cost lives and determined outcomes. The twin Allison engines of the P-38 Lightning produced nearly 3,000 horsepower. Italy's best single-engine fighter managed 1,475. The ratio was roughly 2-to-1, a number that would appear repeatedly in other comparisons, other measurements, other evaluations of American and Italian military technology. The numbers weren't even close. And in their honest assessment of what those numbers meant, Italian engineers provided a service to history, documenting the reality of technical disparity in an age when technology increasingly determined the difference between victory and defeat, between survival and disaster, between competing visions of how the world should be organized and who would have the power to make that determination. The captured technical manual eventually found its way into archives, preserved as a historical document. The engineers who studied it moved on to other projects, other challenges, other phases of their careers. The war ended. Nations rebuilt. New aircraft were designed. New engines developed. New technical challenges emerged and were overcome or accepted. But the lesson remained, encoded in those specifications, preserved in the reports and analyses that Italian engineers compiled during that summer of 1943. Modern warfare rewards industrial capacity and technological sophistication. Nations that can design and build superior equipment in quantity hold decisive advantages over nations whose engineers are equally talented, but whose industrial base cannot support equivalent production. The numbers weren't even close. They never could have been, given the underlying disparities in industrial development, resource access, and manufacturing capacity. Italian engineers recognized this truth, documented it honestly, and in doing so, provided future generations with a clear example of how technical analysis can illuminate larger questions about national power, industrial capability, and the factors that determine success or failure in modern conflict. As the sun set over Guidonia on those long summer evenings in 1943, the engineers packed up their documents, secured their calculations, and went home to families and routines that continued despite the war raging around them. They had done their job with honesty and skill. They had measured reality accurately, even when reality was discouraging. The numbers told a story, and Italian engineers told that story truthfully. The twin Allison V1710 engines of the P-38 Lightning, producing their combined 2,850 horsepower, continued to power American fighters through the skies, over Italy, over Europe, over the Pacific. Italian pilots continued to encounter them, to fight them when they could, to evade them when they couldn't. The technical disparity that Italian engineers had documented in their reports played out daily in combat, a reality that no amount of courage or skill could completely overcome. And somewhere in the archives, in the preserved documents of wartime engineering analysis, the specifications remained, a permanent record of the moment when Italian engineers compared their best fighter engine to the P-38's power plants and confronted the uncomfortable truth that the numbers, in all their unforgiving precision, weren't even close.